before we let you attempt the proof, I would suggest I mention some relevant new rules that you may want you may find useful for your proof for the deadlock freedom, relative deadlock freedom in the case of refinements. So this will be our set number 3. Remember, we actually gave you 2 example sets of inference rules already. This will be set number 3. I'll make sure I also include a link on the lectures page about the PDF, so you can definitely refer to either of the 3 sets anytime. Right, so for this set, we only got 3 rules to really go over. They are incredibly useful, actually, for each one of them. I would suggest look at the rule yourself and also read over the description. What I will do is I'm just going to go over on the iPad very quickly together with you, just about some intuition. Right, let's now go over this. The first one here is about ORR. So that means the disjunction appears on the right-hand side as the go over here, disjunctive go. That's what we have. And what we are really saying is, if you got some disjunctive go, you can choose maybe one of the disjunct over here and move that as the hypothesis, but you want to make sure you kind of negate it, right? That's really the rule. Of course, you gotta know the pattern. But how is there any justification we can give in order to justify this particular rule? Yes, we can. Let's do that little proof very quickly. I just want to convince you. So this part over here, we know that the turnstile simply implies. So what we got is we got H implies P or Q over here, and it is equivalent to, right? We're doing the equivalent equational style of the proof. So we know the definition of implication. Do you remember what it is? So if we got, let's say, X implies Y is equivalent to not X or Y, right? So that's the thing. That's the definition you should know actually from your earlier course of math, right? So according to this, what we have is not H or P or Q over here, and we can definitely try to bracket the disjunction maybe this way over here by its commutativity property, right? So here we can say equivalent to by the commutativity of disjunction. If I have X or Y or Z, equivalent to if I bracket X or Y and or Z, right? By that, I'm gonna get not H or P or Q. Right? So far so good. And we know double negation. Right? Double negation. Which is about P is equivalent to not P. Right? Which I'm gonna do for this one here. Right? How do I do that? I can say not H or P or Q. Right? And you can see this part over here, the inner negation, we can apply De Morgan. Right? Let's now go further. I'm going to make the proof a little bit smaller front in just at the end. Equivalent to. And then we can apply De Morgan. De Morgan. Which is about, if I say not X or Y, equivalent to not X and not Y. Right? For that one, we're going to get not, and you can see not H. That's just another double negation, right? Let's document it as well. That's also by the double negation. Double negation, right? Of course, when you justify it, you want to make sure you write down the full name. But for now, you know the context. Right? So not and not H is going to be H and not P. Right? So far so good. And or Q. Right? And now we are achieving some form that looks very promising, because you can see that it's exactly the not something or something. So that's exactly matching the definition for implication, right? So what we can do is we do another application of the definition of the implication, right? Which I already wrote down over here, right? So that will be exactly H and not P implies Q, right? You can see here H and not P, exactly the comma over here. The next inference rule actually will show to you over here. The comma over here really is about conjunction, right? That's something you should know. I think that's something I mentioned also earlier, right? So the comma over here in the hypothesis will just be conjunction, meaning that we want this hypothesis and this hypothesis. So H and not P will be equivalent to H comma not P, and also turnstile Q. That's exactly what we have, right? In order to prove this, it will be equivalent, it will be sufficient to actually prove this. That's exactly what we're showing, right? Let me make this just a little bit smaller over here so you would know this proofs really belongs to the first inference rule that we are trying to justify. Okay, let me put it here. And of course, let me just box it just to make sure. Okay. And this is the justification for this particular inference rule. All right, let's talk about the other two. The next one over here is about the syntax, really. If I got Q and P and Q, like a conjunctive hypothesis, it can be split into P comma Q. That's exactly what I just mentioned. This one is straightforward. And the reason that it's actually called underscore L over here is actually because, let me write it down explicitly, underscore L, because the conjunction appears exactly to the left of the turnstile. That's why. All right. And let's look at the last one. This last one is called and also underscore R. That means the conjunction appears after to the right of the turnstile. So we got a conjunctive go, right? If you remember before, there is another inference rule for which we can actually split the original sequence into two separate sequences. If you can remember, right? I'm gonna write it down, and then you can actually look it up yourself. Okay, look it up. This particular one, I believe it's called the ORL, right? So for that one, there is really about disjunctive hypothesis appearing to the left of the turnstile. In which case, you will be able to split it into two sequences, right? So this is just another rule where we can split the sequence in a different way. All right. So there's a little bit exercise for you to complete. Look it up over here. It's up to you. And then how do we understand the current one? If we got a conjunctive go, P and also Q, that means we want to prove both the P and the Q. In that case, we can prove them separately. We can prove P and also prove Q. And that's why I really want you to really compare and contrast this rule over here against ORL. Because in that case, if we got a disjunctive go, let's say P or Q over here, in that case, we're going to split it also into two sequences, but P will be hypothesis over here, and the Q will be hypothesis over here. Right? That's something I want you to clarify for yourself. Right? So these are the three rules that we're going to find useful for our relative deadlock freedom proof. Right? Review these rules and make sure you got all the three sets of example inference rule handy. Whenever I want you to do some proof exercise, you should always think about which ones might be relevant. All right, let's now move on to the proofs.